visible.
Okay, thank you. So, very good afternoon to 100% here. So, it's my pleasure to join with you. And today we're going to see about Bloch sphere, what Nivedita mentioned. So, to understand quantum, to understand qubits, understanding Bloch sphere is very easy. So, take an example of a 3D sphere. 3D sphere will act like a Bloch sphere, which is a visualization tool for a quantum particle. Okay. So normally the Bloch sphere will have the radius equal to 1. Okay, so we try to normalize that sphere, so the radius will not go beyond 1 or below 1, so it will be very constant. So that is why we are using a unit radius for Bloch sphere. So dividing this Bloch sphere into two hemispheres. Okay, dividing this Bloch sphere into two hemispheres. So why we are dividing the Bloch sphere into two hemispheres? Because we want to attach binary logic, two-level system with qubit. So as we discussed in previous session, if you are able to divide your qubit into 3 levels, then you are able to represent trinary logic. So far we are representing only 2 logic. That is why we will be 2-level system. So it is possible in quantum to increase number of pieces. So you can increase up to n number of pieces. So this is one good thing about quantum. So next, as usual, we are having 3 axes, like 3 coordinates. So x, y, z, like a Cartesian coordinates. So this will act like a reference from origin point. So from the center of the sphere, we are able to originate 3 axes, which will act like a reference. Normally we call it basis states. Okay. So imagine 2 extreme points, one point at north pole and one point at south pole. Okay, these 2 are extreme points in this whole sphere. Okay, for 2 hemisphere. And these 2 states will represent like pure states, these polar points. Okay, this will act like a pure states. So take any point inside your sphere, apart from these polar points. Okay, take any random arbitrary points inside the sphere, and this green dot will act like a quantum particle. Imagine if you are considering an electron, position of an electron. Okay, this green dot is representing position of an electron or any property of a quantum particle. If you are generating a vector from the origin, okay, it will point out that quantum particle. So generally, this blue color vector will represent quantum state vector. It will give information about your quantum particle. So imagine like this. And what we are doing, we are calling this point as a mixed state. Okay. Is my voice audible? I have full voice. Am I audible? Okay, great, thank you. So this point you can call it as mixed state, and you can call it as a superposition state. So it is not exactly in state 0, not exactly in state 1. It is in between. Okay. So whatever if you are studying superposition, you can visualize in this. So this is a 3-dimensional view about a quantum particle. So next, what we do, we try to slice that sphere from that point. So it will make x dash and y dash. We are making a projection from this point, from this plane. Okay. So make a projection from that gray dot to your xy plane. Okay. So this is one type of projection. From this intersection with your xy plane, make a projection to your origin. So we have 2 projections from the green dot to xy plane, right? Volume of voice is low. No, I'm audible. I kept all settings full, right? So this will make a right angle triangle. These two projections will make a right angle triangle. Okay. So when you have right angle triangle, you can apply trigonometry and you can apply trigonometry. You are able to convert Cartesian coordinate into polar forms. Okay. So this state vector will make an angle from your z-axis. This is called theta. And from x-axis, the downside projection will make psi. So we have two angles. So why we are making two angles? To convert a Cartesian coordinate into polar. So this is our objective. So if you want to represent any quantum particle, if you want to represent in equation form, okay. So this is the formula. This is the formula. So this psi represents your wave particle equation. Okay. So this will represent your quantum particle. If you want to define, you need to know how many states it could exist. So how many basis states we have? State 0 and state 1. So that is why we have two components over here. So that is why we have two components over here, cos component and sine component, where cos component is related to state 0, sine component related to state 1. So why we are putting plus? We have, because it is a linear combination. So how many quantum states your quantum particle have? We need to add all these quantum states together. Okay. So normally it is considered like basis. So we have two level system. For two level system, we have two extreme points. So these two extreme points will act like a quantum basis for our chosen example. Okay. So consider theta equal to 0. So refer previous slide for your understanding. I'm going back. Okay. So look at here. So this is theta. So theta is the angle between your z-axis. It is computational basis to your quantum state. Okay. So remember this. If theta equal to 0, imagine where it will point. If theta equal to 0, great. So it will point to state 0 in this z-axis. Exactly. Okay. So apply theta equal to 0 in this formula. Apply theta equal to 0. Cos 0 by 2 multiplied with state 0 plus e to the power I sine 0 by 2 multiplied with state 1. So we have a complex number. That is why we have imaginary part. Okay. And we are playing with two angles. One is theta, one is psi. Okay. So cos 0 by 2 will turn into 1. So 1 multiplied with state 0, you will get 0. So sine 0 by 2 will turn into 0. So 0 multiplied with state 1. The whole component becomes 0. Okay. So sine part is eliminated. You only got cos component. That is why you got state 0. So what it means? You are applying some operation over your quantum particle. Okay. So what type of operation you are applying? You are applying theta equal to 0. So it means you are applying identity QT. So this is nothing but, this operation is nothing but you are doing identity operation. So what happens if you apply identity operation? State remains same. So this is nothing but your pass operation. If you are doing some pass operation, so what happens? Nothing will happen. The state will retain same as it is. Okay. So this is an example. If you apply theta equal to 0, the quantum particle will remain in the same state. So is it clear? Shall we move further? Very simple. Great. Okay. Thank you. So next, what are we going to do? We apply theta equal to pi. So what happens if you apply theta equal to pi? So whatever you do in quantum, you can visualize through mathematical way, or you can visualize through Q speed or Bloch speed. So both ways you can do. Okay. So initial stage, you go through Bloch sphere. It is very easy to visualize. You'll know what happening when you apply an operation for a qubit. Okay. But mathematical representation will lead to much more complex states. So if there are multiple complex states, visualization will fail. Okay. So normally for few levels, you can go with visualization. For multiple states, complex system, you need to do with your mathematical structure. So I request you, all of you, go through visualization first to understand basics of quantums. Right. So apply data equal to pi. So cos pi by 2 multiplied with state 0 plus sin pi by 2 multiplied with state 1. So in this version, cos component becomes 0, sin component becomes 1. So you'll get state 1 only. So what it means, if you apply data equal to pi rotations will happen for your quantum state vector. So initially it is pointing to state 0. So this is our original quantum state. If we apply data equal to pi, you can visualize like this. So we are looking for the first angle. We are not looking for second angle. We are not applying the second angle. We are applying only first angle. Okay. So remember, if data equal to pi, we are applying the rotation only for the first angle. So which is nothing but it will do bit free. So this gate is equivalent to your NOT gate, classical NOT gate. So this is classical. So previous example, data equal to 0, identity gate. In this example, data equal to pi is NOT gate. So both are classical. So we can understand from classical point of view, nothing is new in quantum. Okay. So from state 0, from state 1, if you're applying data equal to pi, what happens? Now your quantum state is 1, exactly. So if we apply data equal to pi, it will go back to state 0. So great answer, right? So next, look at this example. If we apply data equal to pi by 2, please wait for all this explanation. Data equal to pi by 2. Now what happens? Where it goes? 0 means state 0. Okay. Pi means state 1. Pi by 2 means it will go to equator. So observe this visualization Bloch sphere. It will go to equator. Pi by 2. Okay. So 90-degree rotation from state 0. We are able to visualize in this way. So if we apply data equal to pi by 2 from state 0, it will go to x-axis. So this is nothing but your Hadamard gate operation. Hadamard gate operation. Okay. So this will create equal superposition, not just superposition, it will create equal superposition. So what it means, 50% it is related to state 0, 50% it is related to state 1. When you do measurement right now, it will give a random result. Okay, either it will go to state 0, either it will go to state 1. You don't know where it will go. So nobody in this world is able to predict the output of Hadamard gate. Okay, this point you need to remember. So Hadamard gate will create randomness in your qubit. So if you want to do something with your qubit, you need to prepare with your Hadamard. Okay, so initially it will be in state 0 or state 1 because we are preparing qubit. Okay, so that is why we are preparing in pure states. So this point you need to remember. Initially, we are preparing qubit in pure states. Preparing qubit in pure states. Next, we are applying Hadamard gate. Applying Hadamard gate. what it will do, it will create randomness. It will create randomness. Then only we are able to using quantum hardware. So this point is very important, right? Suppose if you are looking at the second angle, psi equal to pi by 2. Now look at that example. Maybe I will highlight. So look at here, psi equal to pi by 2. Now the second angle is going to take part. Okay. D equal to pi by 2, also psi equal to pi by 2. What happens? It will go from state 0 to x-axis. Then it will do rotation in xy plane. It will land up in y-axis. So x-axis is real axis, y-axis is imaginary axis. That is why whenever if you are dealing with second angle, it will include imaginary component. So is it clear? Any doubts? Shall we move further? Okay, great. Thank you. Thank you. So next, we can visualize the Q sphere in this way. We covered state 0, state 1. So state 0, state 1, normally it is called computational basis. Computational basis. Okay. So plus and minus consider as real axis, or you can say real basis. Okay. So y-axis you can consider like imaginary axis or imaginary basis. So we have 3 axes and we can form 3 pairs. So state 0, state 1 are opposite in nature. So plus state x-axis and minus x are opposite, I and minus I are opposite. So we have 3 pairs. With the help of 3 pairs, you can represent any point in your Bloch sphere. Okay. So imagine this is your Bloch sphere. Okay. How will you represent state 0? So look where your state 0 represent. It is in North Pole. So it is in North Pole. So this is Northern Hemisphere and this is Southern Hemisphere. So Northern Hemisphere related to state 0, Southern Hemisphere related to state 1. So look at here, if you want to represent state 0 in matrix form, the upper component is 1. Sorry about that. The upper component is state 1 and lower component is state 0. Because state 0 only have relationship in Northern Hemisphere. So that is why we have column vector where state 0 represented as 1. Can you tell what could be the representation of state 1? If you understand this one. 1, 0. Great. So we'll clear this. So state 1 you can represent as 0, 1. Okay. So this is ket vector. So this is ket 1. Or you can say ket. So there is an opposite nature of ket 1, which is bra 1. You need to reverse 0, 1, like a row vector. So this is column vector. This is row vector. So you can represent in any form. Okay. According to your operation, you are able to represent in any form. Okay. So linear 90-degree means this is 2-dimensional. So this matrix represents 2-dimensional. Great question. So imagine state 0 and state 1. Okay. So what is the angle difference between state 0 and state 1? 90 degree. So 90 degree we have linear. So this is what it means. Now look for plus state. So if you apply Hadamard from state 0, it will go for equator. So look at plus state. So where it is located? In equator. Okay. So what is the relationship between state 0 and state 1? Okay. It is in between. So that is why both components will be 1 for positive state. Not exactly in 0, not exactly in 1. That is why both hemispheres are related to plus state. Right. So you can look like this 45 degree. Exactly between state 0 and state 1. So this is 3-dimensional. This is 2-dimensional. So is it clear? Any doubt? Okay, great. So look at the component 1 over root 2. 1 over root 2. This is amplitude of both signals because it is in equal superposition. So this will come equally 1 over root 2. If you apply modulus to this, okay, if you do square, it will give 0.5. Okay. So next, look for minus state. So minus is exactly opposite to plus. Imagine this is plus, this is minus, which means opposite side or opposite in nature. So how will you differ this representation with this? You are negotiating the second component as minus. So it indicates it exists in opposite side of your sphere. So that is why the second component become minus to represent the opposite nature or opposite side. Fine. So next, if you look at y-axis, I component, the second component we are denoting with I. Okay. In the same way, minus y, you are representing with minus I. The second component become minus. So this is how we are able to understand how to represent here Q sphere, qubit in your Bloch sphere. If you do any operation, you are able to visualize your Q sphere. And this is the mathematical representation. In multiple ways, you can visualize your Q sphere, either by visualization or either by mathematical structure. So whatever you do, the operation will go circular clockwise because the rotation will go in angular rotation. Okay, so not it will go in linear form because it is a sphere. So imagine like this. So this is the alternative view, how we are able to view all your quantum state in matrix. So this is the great tool. What I suggest each and every one of you go to this tool. I will share this link with you. So go to this link. Are you able to get this link? Please put something in chat. I'll repeat all this content, maybe multiple lectures, they will cover this topic. So no issue. Everybody will explore in their own perspective. So it is good to revise, right? So look at this web page. So here you can see state 0 and state 1. This is for pure states. This is for pure states. If you want to prepare, or initialize your qubit then you need to click state 0 or state 1. So this is up to you. Either you can create your qubit in state 0 or state 1, but definitely we need to create in pure basis tree in quantum. Why? Because if you are creating a quantum bit, okay, a random state, if you don't know what is that state, you don't know what is the operation you are going to make, what is the output you will give. So it is always suggested to create a quantum bit in pure states. Otherwise, we don't know what is the operation we did, what is the output we got. So state 0, pure state, apply X gate, click X gate. What happens? The bit flip will happen. So state flip will happen. So it will convert state 0 into state 1, 5 rotations over Z axis. Okay. So this will. So next what you do? Apply X gate from state 1. Okay. It will go back to state 0. So apply X gate to state 0, which will lead to state 1. Okay. Apply X gate to state 1, it will lead to state 0. So what it means? Consider your quantum state is psi. Okay, quantum state is psi. If you are applying X gate, again if you are applying X gate, these two X gate will cancel each other, which will bring back to original state. So 2X gate, next to next will cancel each other. Okay. What it means? X gate have own inputs. So this is what it means. If you apply X gate, immediately if you apply one more X gate, which will cancel each other, you will go back to original state. So if there is any situation, if you are applying two NOT gate, okay, try to avoid, because your quantum state will go to the original state. No use of applying two X gate next to next. So any doubt until this? Great. Okay. So click state 0. Okay. Click Y gate. Observe what happens. So it will do bit flip exactly like NOT gate. Okay. But you can see difference in phase. So this is the phase disk. You will get pi by 2 phase rotation. So visually you are not able to see, but downside you can see change in phase. So X gate is NOT gate, Y gate is NOT gate along with phase flip. You can say phase flip. The value is pi by 2. So this gives additional freedom for you to do more operation. So NOT gate, you don't have any additional freedom, any additional changes. But in quantum, we have X gate, NOT gate, exactly like classical, but Y gate will give additional freedom. You can do a bit flip about pi by 2. So more freedom, more computation you can do. So this is the point I want to highlight. So remember, quantum always give the additional freedom, the additional movement, which will do additional computation. Yes. So next, look at the Z gate. So click stage 0. So same, sorry. Click stage 0, apply Y gate, you will get bit flip. Again, apply Y gate from state 1, you will go back to original state. So applying 2Y gate, next to next will cancel each other, which will bring back to original state. Exactly like X gate. X gate and Y gate will cancel each other. If you apply twice, next to next. Okay. So apply Z gate. I will cover, please wait. So apply Z gate from state 0. Are you able to see any changes? Apply Z gate in state 0. Any changes are able to see? No. Z gate will not do anything in state 0, in pure state 0. Okay. So apply NOT gate. Now it is in state 1. Now click Z gate. Are you able to see any changes? Apply Z gate. There is no physical changes, but look downside, you can see a bit flip about 5 rotations. So phase flip, phase flip. So Z gate will introduce 5 rotations any point in your Bloch sphere except state 0. So Z gate will do phase flip for 5 rotations except state 0. So this is the point you need to remember. Okay. So remember in this way. Okay. So X gate, which will do bit flip, classical NOT gate. Y gate also do like X gate along with phase flip, pi by 2 rotations. Z gate will do pi by 2 phase flip. Okay. Across all point in your Bloch sphere except state 0. So Z gate will not act on state 0. Okay. This is the important part. So apply Z gate next to next will cancel each other. So we covered three gates, X gate, Y gate, Z gate have own inverse. Okay. So next, click stage 0. Apply Hadamard gate. Remember what happens? When you apply Hadamard gate, what will happen? Randomness. Hadamard gate will create equal superposition. So always you need to remember, Hadamard gate just not create superposition, but it will create equal superposition like a fair judge. So 50% away from 0, 50% away from 1. If you do measurement after your Hadamard gate, will give random binary value, either 0, either 1. Nobody able to predict. Okay. So that is why if you prepare stage 0, apply Hadamard gate, it will go for plus x-axis. Okay. Again, if you apply Hadamard gate from plus, what happens? So apply Hadamard from plus state. Exactly. So it will go back to original state. So stage 0. Okay. Apply Hadamard. Okay. What happens? It will go to positive state. Okay. It will go to positive state. So apply Hadamard to positive state, which will go back to state 0. So applying two Hadamard gate next to next will cancel each other. It means Hadamard gate also have own inverse. Okay. Now what do you do? Click state 1. Apply Hadamard gate and tell me what happens. Okay, I will tell. Click state 1. Apply Hadamard where it is. Do and tell me. Minus state, exactly. So from state 1, if you are applying Hadamard gate, it will go to minus because each and every quantum operation should be differentiable. So from state 0, if you apply Hadamard, it will go to positive state. From state 1, if you apply Hadamard gate, it will go to negative state. You can see difference between operation based upon difference between your initial quantum position. So if it is differentiable, it is reversible. So quantum is very good at reversible computing. Reversible computing. Okay. Take an example of unkk. Take an example of unkk, x, y output. Okay. For stage 0, 0, you'll get 0. 0, 1, you'll get 0. 1, 0, you'll get 0. 1, 1, you'll get 1. So if I get input combination, okay, you able to predict output. Suppose if I'm giving output combination, can you predict input? Is it possible in AND gate? Suppose the output is 0. Okay, you cannot predict because 3 input combination leading to same output 0. So this will make confusion because you lost your information. Okay, you lost your information. You have two inputs. But you got only one output. You got only one output. You are losing your input combination, your input information. You are not able to get output because the output are not differentiable. Only one state you are able to define. Okay, if output is 1, you are able to predict input combination only at one scenario, but not for all combination. So this will happen in OR gate also. So try to do for OR gate, you cannot predict the input combination. Now look for NOT gate. So what happens? X is your input. Okay, you'll get some output. If you are given 0, you'll get output as 1. Okay, if you are giving 1, you'll get output as 0. These two combinations are differentiable. So if it is differentiable, you're able to predict, you're able to do reverse computation. You're able to know what is your input if we have 1:1 ratio or n:n ratio. So this is your input, this is your output. So in quantum, how many inputs you have, the same number of outputs you get in ratios. So that is why no information is lost. You are able to go back to previous state. So any doubt? So how quantum gates are useful in reversible computation? This is the important property in quantum. That is why we are using quantum. Any doubts? Shall we move? Right. I will tell subsequent gates. Stage 0. Okay. Stage 0, if you click yes, Hadamard gate. If you click Hadamard gate, okay, it will come to positive state. Then what you do? Try to implement yes gate. It will do pi phase rotations in xy plane. Sorry, pi by 2. Okay, so we are dealing with the second angle like the previous slide. Are you able to recall? Right? So stage 0, what we did? Stage 0. Then we applied Hadamard gate. It will go back to positive state. Okay. Then we applied S gate. Then it went to state Y. State Y means plus I. Okay. So do one more escape. Observe what happens. It will go to minus. So S gate doesn't have own inverse. If we apply 2 S gate, it will go different location, which will not bring back to original location like all these 4 gates. So S gate doesn't have one inverse. That is why we are creating a new gate called S dagger. So this will look like a cross. This is called S dagger. So S dagger is inverse for S gate. So if you want to do reverse operation, you need to do S dagger. If you apply 2 S gate, you will not get back the original state because the rotation is pi by 2. But for all these gates, it will do pi rotations. Okay. Is it clear? Okay, great. So click stage 0. Click stage 0. Apply Hadamard gate. Okay. Apply T gate. We can see some little difference between S and T. So T is nothing but it will do half rotation of S gate. So how to relate between S gate and T gate? 2 T gate equal to 1 S gate. Exactly. So this will make 45 degree. This is equal to 1 T gate will do pi by 4 rotations. Okay. Again, if we apply T gate, it will go back to I state, plus I state. Okay. So 1 S gate equal to 2 T gate. So more number of operation you can do in quantum. Okay. You can fine tune your rotations. So you can do more operations. So this is the logic you need to understand. The more degree of freedom, the more computation you can do in quantum between stage 0 and stage 1. Okay. So click stage 0, apply Hadamard, okay, apply Z gate and tell me where it goes. So this is the question. Stage 0, apply Hadamard, okay, apply Z gate, where it goes. Minus T. So why? If you apply C gate, it will do pi phase rotation. Are you able to recall? So Z gate will do pi phase rotation. Okay, that is why going for opposite side of that sphere. So multiple ways you can do quantum operation. You can jumble your gate sequence. So the same operation you can do with less number of gates. So this you need to think like a Boolean algebra. You try to minimize your gates so that your quantum operation will become much more fast. So please make this point. So Rx, Ry, Rc are more fine rotations. Great question, by the way. So you can do pi by 8 rotation. Okay, you can do pi by 12 rotation. So more fine tuned you can do rotations. So if I'm clicking here, so you can see more fine tuned. I am applying pi by 8 rotations. Are you able to observe? Okay. So click stage 0, apply pi by 2. See, you can see more finer rotations. More control you have. Okay, great. Now we're going to look about a new tool. So most of you are requesting this tool, okay, which is very helpful if you want to work with QuizKit with multiple versions. So a lot of people we have confusion which QuizKit code we need to run on which kernel. So installing and maintaining different version is really challenging because QuizKit, IBM QuizKit, they are keep on upgrading. So it is very challenging for professionals also. So what I suggest, each and every one of you, please go to qBraid. So use your Gmail account to log in. So go to login account. So use your Gmail. Are you able to log in? So go to launch lab. So here you can see so many varieties. GPU, you can use GPU. You can use Intel quantum computer, right? So many options are there, which is very good. So use free 2V CPU, which is nominal. Try after sometimes. I will share this link with you. qBraid. Even for me, it is showing some error. So sometimes it will happen. So don't worry. Today it is taking a lot of time. Maybe multiple people try to log in. Click free CPU version 2. Wait for some time, it will work. Otherwise, you refresh. Anyway, if you go to YouTube, they are giving so many tutorials how to use qBraid. Otherwise, I will share with you step-by-step details. So after this session also. So this is how the dashboard will look like. Exactly like your Jupyter notebook, like your qBraid. Yes. So very easy for you. Okay. The good thing is you can run multiple Qiskit versions. Okay, so most of the hiccups will happen because they are frequently changing the kernel version, software version. Very difficult to find out which one will work and difficult to install and run your. So what do you do? Go to environment. So click environment manager. Click environment manager. Okay. Add environments. So you can have variety of quantum platforms. This is really good. I really recommend each and every one of you. So go here and try to install kernel, which is the oldest version of Qiskit. Yeah, you can work in any folder also, but this I recommend personally. Okay. So here, what you do? Search for Qiskit 0.420. So try to install this kernel, which will support the older version of books. What I shared with you, 3 notebooks, you can run all those notebooks with the help of this version. So once you add that, you can see Python 3 Qiskit code. So once again, I will tell, once you log in, you can use Launchpad, okay, use free 2V CPU, 4 GB RAM. All of you able to do? If it is not working, wait for some times, it will work. It will take some time. Okay. So once you install, you click Python 3 Qiskit, Python 3 Qiskit. So go to the code, what I already shared with you. You can run all those code very easily without any error. Okay. So select all these code snippet. So put in your qBraid environment, Jupyter notebook. Okay. So click environment, it will go this side. Click files, this will go this side. You will have proper Jupyter notebook kind of thing. So executed without any hiccups, very easy for you, right? So come down, scroll down, copy this code also. So once you execute the code, if you want to know what is happening, so try to print that object. Print circuit. See, this is how we are able to visualize then and there. So whenever if you are giving yes, each and every command, make sure it is executed. So look at this code, very simple. So what we are doing, we are importing NumPy, okay. Then we are importing Qiskit libraries, packages. Then in cell number 2, we are creating a quantum circuit by a function call. So quantum circuit is the function call. For that we are passing value 3. It means it will create 3 quantum bits in a quantum circuit, and your quantum circuit name is CIRC. So this is the object created by this function call. Okay. So we try to print that circuit. Next, what we did in cell number 4, we are we are putting a Hadamard gate in Q0. So this is what it means. Maybe I will use highlighter. So H 0 means we are putting a Hadamard gate in Q0. So next CX 0, 1 means we are implementing a control NOT gate. So control NOT gate we already covered in last class. And next what we are doing, we are putting one more control NOT between 0 and 1. So this is your object reference. Okay, if you want to do in-depth analysis, we can note down this reference code for yourself. So next, what we try to do, we try to visualize that circuit with help of this code. We can use, you try these versions, you try and explore. If any error is popping out, try to resolve. So some version it won't go. That is why I prefer the oldest version. It is up to you. So here you can change text. So your output will be changed into text version. Okay. Next, what we can do, we can use latex. You can have output like a latex documentation. So multiple ways you can use draw function based upon your parameter. Okay. So next, what we do, we try to print the quantum state vector. Okay. So we try to print that matrix, what we cover. So if we are running latest version, it will show error. Okay. So wait for the solid dot. Okay, it is executing. So cell number 8, we are importing AER module from Qiskit package, right? Then we are calling quantum state vector simulator. It is one type of simulator available in this package, and we are using it like a back. So we can use simulator and we can use real-time quantum hardware. Okay. So try to run, make sure it is executed. So try to print backend. Again, backend is an object. Still it is executing. Today it is taking so much of time. Okay. So what I will do, I will show the already executed code. And you will face so restart and run all cells. Taking little time. Let's see. Okay. So in this way, you are able to execute all your codes without any hiccups. So try to change your kernel, try to run your code. So if any error is happening, look for Qiskit forum. People are ready to help. Right. So one more tool I want to introduce, Qniverse. So this is the tool created by our C-DAC. I'll share this tool with you. .42 you can use, or 0.43 you can use, or 0.17 also you can use. So all of you go to this link. This tool is developed by C-DAC and they are giving access to it. So in future, all Indian quantum computer, government official quantum computer, we are able to access through this QUniverse. So to get access, click this link. Okay. You need to enter your detail. Who are you? Your email ID, phone number, whether you are working professional or student. Okay. And your level of expertise and why you are looking. If you mention all this stuff, they will give access code to your mail ID, right? So create a login, wait for some time, 1 or 2 days. Sometimes within single day, they will give access. And this tool is very cool. Very cool. So you can have the similar kind of framework like Qiskit. So okay, the C-DAC tool also similar to Qiskit. If you are familiar with Qiskit, this tool is very easy and convenient for you. And it contains more additional features. If you come down, you can see probability distribution. In Qiskit, it is different. Okay. Here also you can change basis also. Okay. So they are developing this tool in very nice way. So as an Indian, we need to support this tool. So click over here, you can see multiple varieties of kernels. Okay, you can use OpenPassing, you can use Google Circuit, and you can use Amazon QT-02. So multiple tools you are able to use within a single interface. So this is the beauty about this Qniverse. Okay, in Qiskit you have only two options. Either you can use IBM Quantum version, Qiskit version, or OpenPassing. But here you have 5 different types of multiple versions. So one is editable, one is non-editable. Okay. So drag and drop any circuit, NOT gate, control NOT gate like this, and try to change your version Google Circ. All your coding will be converted into Circ platform. Again, Circ also using Python. So if you are familiar with Python, so no hiccups will happen if you switch on multiple platforms. So this is what I suggest. Okay. So go to view, go to file, go to view, go to help. You can see lot of documentation, right? Go to settings. You can run that circuit in GPU. They are giving GPU access, very good for us. And they are giving vector form. So you can use the HPC. So much more powerful your execution could be if you are using simulator. And in future, they are giving quantum processing. So far, they are not offering, but in future, they will integrate. Maybe from IASC or from Tata Institute of Fundamental Research, they will integrate. So go here, you can change your profile information and click this sidebar. Click this sidebar. You can have multiple resources, computational resources. So these are the resources provided by C-DAC. They have a partnership with NVIDIA. Okay, they have partnership with Amazon. So click here, go to algorithms. So in upcoming sessions, you are about to study algorithms. So all these algorithms, you can have predefined programs or libraries. If you want to study about an algorithm, this is very beautiful platform. What is this? So for an example, if you want to understand Dash-Joseph algorithm, the input is 2 qubits. You can select the function type also. Okay, you can load the circuit. So automatically this framework will load the entire algorithm for you. You can modify little bit in your algorithm. You can easily do. I love this aspect. So they developed in very beautiful way. Today it is taking a lot of time. I don't know whether so many participants are trying. Okay. So by the way, you can use this tool. I can skip. Next, what I want to introduce one more tool from our Indian ecosystem, QC. So this tool is developed by IAC Bengaluru, IIT Kharagpur, and C-DAC. So this tool also very nice. This one. So use your Gmail account, you are able to log in. Okay. So you can select multiple HPC. So Param Shakti, Param Utkarsh, we can select. So these are supercomputer built by C-DAC, right? So here also, if you know Qiskit, if you know Python, everything is similar. So knowing Qiskit, you have multiple advantage. You can use both tool developed by our C-DAC and IIC Bengaluru. Okay, they are giving lot of examples. So click examples. You can see so many programs, algorithms. Again, it is very easy. So you can construct the full ladder. Comparatively, it is easy for you. So you can have lot of examples. So this is the full ladder code. You can run this code. You can look at your output. So if you know a single framework, you can run multiple loops. And they are giving lot of options. So you can introduce noise parameter over here. Okay. And simulation, you can do plotting, you can show partition, you can run on GPU. Okay. So before 6 months, IIT Kharagpur, they conducted 1 month course about QC. I participated in that, right? So please make it popular among your student community about both tools. These tools are generated by our Indian government. So we need to use as much as possible. So this is the quantum circuit, what this algorithm generated, coding generated. Okay. And go for the documentation. You can have lot of documentation. Easily you can copy code from this. So if you are struggling with quantum gates, okay, this will help you. Right. And this is the status of my job. Okay, I submitted on 16/4. So before 3 days, I submitted only 42 seconds to complete the entire. Very nice tool actually. So if you are writing for journals, the output will be very superb. You just download this image, include in your journal paper or conference. And one thing I want to mention, from IAC, they developed DM module, which is very new in Qiskit. I will share that link with you. So IAC developed their own noise model. So you can have a detailed paper. I share that link with you. And it is integrated in IBM Qiskit also. Whether my link is visible, the paper, what I share. Okay, great. Thank you. Thank you. So we discussed about Qiskit. We discussed about qBraid. Let's see output of a qBraid. Go to kernel, restart all cell, run. So whatever I shared in first notebook, you able to see all output over here. Pending I will cover in next session. Okay. Thanks for asking. Are you able to get output? See, you are able to get the output. Okay. So these two packages are important. If you are getting any error, please try to install IPY widgets. Okay. Then one more package, Py Latin ENC. So I will share these two packages in chat box. Sometimes you need to troubleshoot whatever the support they are giving. If they keep on changing the version, we need to do some little troubleshoot. And if you want to know your Qiskit version, okay, you can use this code. So better read documents before running any code. What is the version they use and what are the kernel you are using? Then only you are able to know all your hiccups. Is it clear? Shall we move further? If you have any doubt, you can ask. A platform I cannot suggest. It's up to you. If you already installed Qiskit in your laptop offline, you can use it. But if you are using multiple from multiple examples, if you keep on changing your kernel, use qBraid. It is easy for you to switch your kernel to switch version between QSKIP. So if you're installing a lot of time, you need to struggle to change your kernel, update and restart your kernel. Yeah, QSIM also so circuit, not like qBraid. Each and every platform have one advantage and disadvantage. So make sure which version your platform is supporting. So according to me, qBraid is so advanced. You can switch multiple kernels, multiple versions easily. Okay, good. So what we do, we try to start with yes, very simple game. We are creating quantum circuit 1, which means it will create only one quantum bit. And what we are doing, we try to put a NOT gate. Okay, we try to put NOT gate. So what I do, I will execute this, then I will execute this. Now you can see changes in your object reference ID. Try to draw this. So this is our circuit. So we added one NOT gate. We try to draw that circuit in MLP, sorry MPL. So we implemented NOT gate in QC. Then what we are doing, we try to do simulation. We are not actually using quantum hardware. We are using simulator. And we are executing the circuit in this state vector simulator back. So try to run cell one by one slowly. Yes, that is why I am telling. Please use qBraid. Very easy for you. Now you can see the output. This is for NOT gate. This is for NOT gate. So make sure you are running code one by one. If you miss intermediate code, you'll get unexpected output. Already you struggle to understand quantum output. So this is an example for NOT gate. Okay, so this is the unitary circuit. So where you can notice matrix like this 0, 1, 1, 0. Okay, now try to change identity gate, nothing. Okay, so delete that NOT gate. Matplotlib, you need to import some packages. So look at the chat box. Look at the chat box. I gave second package, right? py latex enc. So try to install that, then restart your kernel, then rerun your code. Okay. Simple. So what we do, we try to delete this NOT gate. Now we have empty circuit. Now you have the empty circuit and you try to draw the circuit. Okay, the circuit is empty. Then you try to run all these code once again. Now you are able to see the matrix 1 0 0 1 for identity kit. So whatever we discussed in Bloch sphere, you are able to run a code and you are able to visualize in multiple ways. So what I shared, 3 notebooks able to run in this. So try to change your kernel, execute all your codes. Definitely all of you will get output. See, the output is changed for identity matrix. So what is the value of identity? State 0. So that is why you will get output at 0. Okay. Now what you do? Try to create a Hadamard gate. Try to understand. Try to create an Hadamard gate. How will you do? Circ equal to H. Circ equal to circ dot H 0. Otherwise, directly can add this. So we implemented one Hadamard gate Q0 and try to call simulator state vector. So try to run the circuit from the background. So try to print the job. Okay. So if you don't know what is happening intermediate, use print statement. So that is what I am doing. So you can see entire detail. What is your backend? What is the backend version? What is the job ID? Whether the process is successful or not, the simulation is successful, and how many times you run the code, shots equal to 1. Okay. So you can have the entire detail. So this is very in-depth detail you can get from this command, right? And you see what is the output you got? Matrix 1 over root 2. Okay. So this side 0, this side 1 over root 2, 1 over root 2, 1 over root 2. So from all real part, you'll get 0.707. qBraid you can run hardware also, no issue. Depends upon your coding. Okay. So try to run this output and you can see Hadamard. So Hadamard will create equal superposition on what is the value called only in the real component, not in imaginary component. Suppose after your Hadamard, if you apply Z, what happens? It will go to imaginary part, right? Opposite side, negative side, right? Then you'll get imaginary. So after Hadamard gate, what you do? Apply S gate, So sys dot S gate so remember what are the operation we did? Do the same way. Why two Hadamard gate applied? Okay, fine. I understood. So run from beginning. Otherwise, we don't know what is happening. So always run from beginning. We implemented one Hadamard gate, one S gate, and we try to run state vector simulator, run the backend, run the job, run the result. Print state vector. Now you can see changes. The second component you will get a imaginary for J. Are you able to see the difference? So 0, apply Hadamard gate, it will go to positive state. In positive state, it will lie over x-axis. X-axis means only real value. Okay, no image. But if you apply S gate, it will do pi/2 phase shift. It will go to y-axis, imaginary axis. That is why you got imaginary component also. So in same way, you can have multiple outputs. Okay, you able to see how it reacts. So any doubt up to this, you can ask me. I shared all this code to the coordinator. They already shared in your drive. Please go and refer your canvas. So don't worry about this. Okay. So we able to know the syntax of any function from Qiskit library. So please go to Qiskit website. They gave all commands and syntax even for the earlier version. You can refer. Okay. So any other doubts? At the type of typing, it won't show syntax because we need to have premium version, I think so. For free version, they won't give. Okay. So I try to run this code. Let's check how it works. So you can have multiple visualization. You can introduce QSphere. You can use Hinton, right? See, the version is not supporting. That is why showing all these error. Each and every time I need to install packages. But if you use qBraid, definitely it will support. Okay, what I do, I try to copy all this code. I try to run in qBraid. All this code I already shared with you, so don't worry. Okay, don't get panic. Maybe we'll start from new because you'll get confused. Okay, we start from here. So what we are doing, we are creating a quantum circuit with 3 qubits. Now we are increasing complexity. Next, what we are doing, we are inserting on Hadamard gate, control node, one more control node. I'll add only those code. So Hadamard gate, control node. So try to understand this logic by yourself, try to visualize. So what we did, we created a quantum circuit of 3 qubits. Then we created Hadamard in Q0. Then we created a control node between 0 and 1. Then once again we created control node between 0 and 2. Okay. Now what you do? Try to visualize it. Try to visualize this circuit. So always try to understand step by step, little by little, easy for you. Zoom out little. Yes. So try to understand this code. So circ h dot h of 0, it means we are putting h in Q0. So this is about first line. Okay. In second line, what we are doing, circ Cx 0, 1. So we are doing circ 0, 1. So this is the mean. So next, what we are doing, circ Cx 0, 2. So we try to associate Q0, Q2. Okay, try to use multiple color for multiple gates. Okay, great question. So each and every time you need to think what is the basic operation of that gate. What is the basic operation of the gate? Okay. So let me cover all Q bits initialized to state 0. So this is the condition. So after Hadamard gate, what happens? It will go to positive state. Okay, entangled state. So 50% for state 0 and 50% for state 1. So you are creating entanglement between Q0 and Q1. Now what you are doing? You are associating Hadamard with Q2. The same operation are you doing in different phases. So step number 1, step number 2. So step number 1, associating Q0 and Q1, it will create entanglement between these two. So in second step, Q0 and Q2, entanglement. So this is nothing but it will create entanglement between Q0, Q1 and Q2. Are you able to get this logic? So entanglement created between 3 qubits with the help of this circuit. So I will tell one more way. Please try to do this. Control node between 1, 2. What mistake I did? I added this gate after the circuit. So always be careful. You start from circuit definition. Otherwise, it will keep on add with your circuit. Okay, no software glitch. Okay, it is my error. Logical error. Are you able to get the logic? So we implemented Hadamard in Q0. Then we implemented control knot between 0 and 1. Then we implemented control knot between 1 and 2. Okay, I tried to explain. So stage 0, stage 0, stage 0. So this will create entanglement. It means Q0, Q1 are highly correlated. Highly correlated. So it means state Q0 is 0, Q1 also 0. Okay. Then this output is given for Q2. We are making entanglement between Q1 and Q2. So by all this way, we try to create entanglement between 3 qubits. Entanglement between 3 qubits. So you can construct the same logic with multiple combinations in quantum, just like classical logic gates. The motto is you need to reduce number of gates and it should be simple. If you are looking at it, it should be simple. So this is simple when compared to previous illustration. Both are same, but you need to think. So next what we are doing here, we try to evolve a quantum state vector. The code is little different over here. Okay. The same operation you can do in multiple ways. So I will remove these comments for better understanding. It will be simple for us. So here we are importing state vector module. Okay, from this package, quantum information package, we are calling from int function. It will create integer value. Okay, so how many values it will create? 2 to the power 3, from 0 to 2 to the power 3. So it is a range. So all these states, all these integer values are assigned to this state variable. Then your circuit will evolve from this value. So there are multiple ways to create a quantum state, either by doing gate operation or either by values. So multiple ways to create your quantum state operation. Now look at your output lattice. So your quantum state will have state 0, state 0, state 0, state 1, state 1, state 1 in entangled. Okay, try to understand this code. So next what we are doing, we try to print array to lattice. Array to lattice. Again, I will remove all these comments already shared with you. So in free time, you please go to it, where you can have a clear idea. So if you have 3 qubits, there are 8 combinations. 8 combinations. 0, 0, 0, 0, 0, 1, until it will go for 1. So all these 8 states combination are located to respective index value. Okay. So what is the state of 0, 0, 0? First question. So what is the location for 1, 1, 1? The last question, 8. Okay. So that is why we have 1 over root 2 at first question and last question. Imagine if you have 2 qubits. Imagine if you have 2 qubits, if you are making entanglement. Okay, what is the entanglement stage? Stage 0, 0 and state 1, 1. Okay, so how many combinations for 2 qubits? 0, 0, okay, 0, 1, 1, 0, 1, 1. But how many states you got? Only 2. So state 1 and state 4. Only 2 states you got in entanglement. So remaining these 2 are in. So same logic you apply for this. So next, actually you can visualize Q sphere in Qiskit also using Python code. So again, it is asking some packages. So what we can do, we can use this C1 package. Yes, possible with 0, 1 and 1, 0. Very good question. So there are 4 entanglement state we can create. So that is an exercise and assignment for you. So try to install that package. Right. Try to run. No. So restart kernel. Then try to run. So what we do, try to run all cells. Again, hiccups there. So this is how you need to troubleshoot. Most probably it will give the appropriate one. So if you little bit Google, you're able to sort it. So I will tell the alternative way. Somebody asked about. Okay. So to implement entanglement, at least we need 2 qubits. Okay. I'll show. Disable the code editor. So this is the entanglement, right? So we have 2 qubits, right? So how many quantum states will get? Either state 0, 0 or state 1, 1. Are you able to observe over here? Okay. So how to create between 0, 1 and 1, 0? Can anybody answer? If you implement any gate, can you transform between 0, 1 and 1, 0? Exactly. Where will you use? Where will you use? Which place we need to place? X is correct, but where we need to place? Q1. Exactly. So drag and drop NOT gate in Q1. You can see the relation between 0, 1 and 1, 0 because so this is state 0, this is also state 0. So after this, what you will get? Either 0 or either 1. So after this, what you will get? You will get state 1. Okay, so there are 2 possibilities. If Hadamard produce 0, so no power supply, okay, it will not come down. Your NOT gate is not activated. Okay, so stage 0 means 0. But if you're implementing NOT gate before this, it will convert into state 1. So what happens? This NOT gate is not active, but even though it will retain the same state. So 0 means 0, 1 means 1. So case 2, if Hadamard produce 1, so power supply will be there. So this is state 1. This will come down. Okay, this will enable this NOT gate. So here already state 1, power supply is there. It means it won't retain the same state. It will convert into state 0. So these two are opposite. So if Q0 is 0, Q1 is automatically state. If Q0 Hadamard produce state 1, automatically Q0 tends to be 0. So it will contradict with each other. So 0, 1, 1, 0. So these two are contradict, these two are contradict. So nice catch up. So if you have, sorry, what is the question? After the H, great. So what do? Drag and drop this NOT gate after this control NOT also. It will work. So multiple ways you can create entanglement. There are 4 different types of entanglement. These 4 different types are maximally entangled. Maximally entangled. So whatever you study in theory in QT-01, you can do practically in QuizKit. So try to use all these gates. This is what you're assigning. So try to explore all these gates. We'll ask question to custody circuit. Okay, we will describe in sentence. Okay, you need to do those problem in circuit. You need to construct circuit out of the question. Okay, we'll stop it here. So thanks for patiently listening all this time. If you are looking at my t-shirt, it is a Q speed, right? So multi-level. So this is the logo of this. I will.
Ashish will answer. Hello, Dr. Ashish.
Sir, I am here.
Okay. Video. Dr. Ashish, I think he's not there. Yeah, thank you so much, Dr. Jaykumar. Thank you for this session, a wonderful session. Actually, if you understand that this is part of the not part of our syllabus, but we wanted to give you a flavor of understanding simulation and understanding various tools that are available to build quantum circuits. So slowly you have got a flavor. So next course, QT-03, Dr. Jaykumar will be taking you slowly. Please don't worry if you're not able to do it immediately. It will take some time. Slowly you can pick up. So he's also going very slow in that sense. But of course, the concepts are difficult. We may have to listen to it once again. Yeah, Dr. Ashish is here. So over to Dr. Ashish. Yeah.
Yeah, so thank you everyone for joining, and thank you especially Jaykumar sir for their wonderful session. And next, I think, sir, we have quiz on this 21st.
Yes, we'll have the quiz on 21st at 4 p.m. The quiz will open. So today, Nivedita madam concluded her course. So she has given 20 questions. You will be given 30 minutes. It will start at 4 p.m. on Monday, 21st. So tomorrow is holiday. So please prepare well. You need to get at least 40%. Getting 40% is not very difficult, but then, if we are not careful, it will be difficult. So please take that seriously. Quiz is very important for getting the certificate. So please prepare well. Please listen to all the material. Please listen to all the, please go through all the material and listen to all the slides, all the recordings, and prepare well. And of course, Jaykumar sir and Mustafizur Rahman, both of them will put 20 questions together. And after Dr. Mustafizur finishes his course, we'll have the exam. The quiz will open after that. So we'll announce the date. Tomorrow I'll mostly today evening I'll post the schedule. Tonight or tomorrow I will post the schedule for the quizzes. And you can, the timetable is with you, so you can take it forward. Thank you so much, Jaykumar sir. And then hopefully on Monday we are taking Penny Lane, right, sir?
Yes, sir. Yes, sir.
So
Thank you. Thank you,
today
sir.
we'll be looking at Penny Lane. In fact, sir will also introduce us to the tool on by DRDO. I think you have given, sir, today.
Today I gave, sir. DRDO 2 tools.
He has introduced. Yeah, so both the tools have been introduced. So you can understand. So he's working with multiple government organizations also, and DRDO was very happy to so that you will go through that tool also. And qBraid also somebody asked, so maybe that also was covered. And we'll have one more session. So I just wanted to add the quiz. Quiz will be starting on 21st at 4 o'clock onwards. You don't have to take immediately. You can take it anytime till 22nd midnight. That is till 11:59 p.m. the quiz will be open. And for anybody who is having any specific problem like health issue or you are not available this 1.5 days, you let us know. You send an email with a genuine concern. If there is anything, we will give you some more time. But otherwise, please, 32 hours is good enough to take a 30-minute exam. So prepare any time. Morning, evening, night, afternoon, whenever you are, you take the exam. So you have 2 nights before you take the exam. So that's I think that is sufficient, and many of them have done. 850 people have got the certificates last time, 865 to be precise. So please take it forward. Thank you so much, Ashish sir, and thank you so much, Dr. Jaykumar sir. We will now have a demonstration on Canvas. For those participants who have a struggle in joining Canvas, please take it forward. Thank you, sir. All of us can leave. The technical team here will take it forward, and they will do the demonstration.